So I tried to pick a selection of topics that would be most interesting to, our corridor of
corridor and all the video viewers. You would be amazed how many we get.
Okay, so our corridor plus everybody who's watching remotely. So I'll start with sandpiles on graphs. This is so I'll work with finite, strongly connected directed graph. So I remind you, this means strongly connected means for all vertices there's paths in both directions from x to y. Yeah, you don't, but ordinary human beings might appreciate it being written both ways. Okay, and we'll say that a sandpile on this graph is just a function sending vertices to non-negative integers. So you could think of the integer at each vertex telling you how many grains of sand you have at that vertex. And what you can do with sandpiles is move the grains of sand around. So you say that vertex V is unstable for this sandpile S if the number of grains of sand there is at least the out degree. So the number of edges VW.
It's a simple graph. There's no parallel.
Yeah, for simplicity, I'm going to make it simple, but that mainly just makes the notation easier.
Yeah.
You can make it be a multigraph, and in very few places will the theory care about this. Actually, there will be one place where it's important to allow multiple edges, so I'll point that out later. And if a vertex is unstable, then we can fire it by sending one chip to each out neighbor. So firing V means sending one chip. I say chip instead of sand grain because it's easier to write and to say, to each out neighbor. And a convenient way to write this down is after you fire V, so you start with this sandpile S, and after you fire V, you'll get a sandpile, let's say, S plus delta V, where this delta is going to be the main player of the first part of my talk. So delta is the graph Laplacian. So it's, well, let me write first how it acts on functions. So if I have a function, say, mapping vertices to integers, then delta f will be another function. And when I evaluate it at vertex v, I would like to get the following thing. So I have to be careful about in and out edges. So I'm going to first subtract out degree of v times v, and I'm going to add, I'm going to sum over in neighbors, so over edges uv, I'm going to add f of u. So this might strike you as a slightly curious choice of Laplacian, right? So here, my negative term corresponds to the out edges from v, but my positive term corresponds to the in edges. So, but it's natural from the point of view of this firing operation. So if I take little delta v to be just the indicator, so this is 1 if w equals v, 0 otherwise. Then, so this definition is cooked up so that when I apply delta to little delta v, I get, well, at a vertex w, I'll get, minus out degree of v. So that's how many chips I'm losing at v. If w equals v, I'll get +1 if w is an out neighbor. And I'll get 0 otherwise.
You want to say something about the history or the motivation of this?
Of the chip firing.
Physics,
yeah, so, okay, so a tiny bit of history. So there's kind of two parallel tracks here. There's Björner, Lovas, and Shor. And then there's Bach, Tang, Wiesenfeld. So these guys, you could say, are in discrete math or in computer science, and these guys are in physics. And I don't think they knew about each other, at the time. And well, maybe at some point they realized they're working on similar things, but they had very different perspectives on the topic. So, from the physics perspective, Bach, Tang, and Wiesenfeld were trying to model self-organization in nature. So they wanted to understand, why is it that you see so many power laws in nature? Why do you see so many long-range correlations? And in particular, when you go and try to make a mathematical model of some physical system, typically you have some parameters in your model, and it's only for very special values of the parameters that you see power laws and long-range correlations. And so they asked, given that that's the case, why would you ever see these in nature? What's the chance that if you just randomly have some system that it just happens to be at this special value of the parameter? So they said there must be some dynamical mechanism where, even if your system starts far away from the critical value, where you see these power laws, it tends to drive itself toward the critical value. And so their toy model of this situation was a pile of sand, and you're dropping sand on top, and every time you drop a sand grain, well, it might fall on top of some other sand grain and kind of dislodge it, and so you would get some trickling of sand down the pile. And you can look at statistics like when I drop one sand grain on top of a large pile, how many other sand grains are dislodged. And that's the kind of thing where if you go and measure this, in an actual desert on dunes, you'll see power law distributions.
What's the graph in this case?
There's no graph here, right? I mean, this is kind of the model in their head, right? And then, they want to turn it into a toy model. So when you turn it into a toy model, it's not very similar to this situation, okay? But this is sort of what inspired them. And their idea was that, well, it would self-organize because although there's one critical slope where you see these special power law statistics of avalanches. So say lambda is the slope of the pile. So here you have a pile that's steeper than the critical slope. Here you have a pile that's flatter. And if you imagine like taking this flat pile and dropping some sand on it, well, you're not going to get any big avalanches, and so your pile will, over time, tend to get steeper, right? So after you've dropped some sand, it will pile up steeper. And on the other hand, if you're too steep, then even dropping a small amount of sand will cause some huge avalanches, and it will tend to kind of flatten your pile out. So that was their idea that, wherever you started at, you wouldn't start at the critical slope necessarily, but if you drop enough sand, you would tend toward it. So the hope, 30 years ago was that this would be like, this abelian sandpile model would be like the one canonical example of this self-organized criticality. And it's a very interesting example, but it's not really canonical. So it has various special features that well, maybe I'll talk about some of them later. But basically, where the field is at now is like there's a whole bunch of variants of this model, and we would like to kind of group them into universality classes and say like, well, all the models like this have the same critical exponents. But it's still debated in physics papers, which models belong to which class. It's all very, we still don't have a good picture of whether there's probably not one, general model of self-organized criticality. But eventually we should have an understanding of, what the space of models looks like. And in terms of Björner, Lovaas, and Shor, what was their motivation? I'm not sure actually. So, it's just some particularly simple discrete dynamical system, and you can ask what it does. How does it stabilize in a finite number of moves, and if so, how long does it take? I mean, that's sort of almost enough motivation. So I should say what I mean by stabilize, right? So this is one move, is firing an unstable vertex, and so you say that S stabilizes if there exists a finite sequence of legal firing moves. Let me see how I did this in my notes. So, I don't know. So say sigma 1 is S plus delta V1, so on. Sigma m is sigma m minus 1 plus delta Vm. And so all these moves should be legal. So that means they really were unstable when we tried to fire them. So say sigma I of V I plus 1 should be at least out degree of V I plus 1. So, and at the end, you can't do any more firings. So sigma m is pointwise smaller than sigma m of v is less than out degree of v minus 1 for all v. So I want to break this up into these two parts, right? So, it's a sequence of firings that accomplishes two things. One is, each firing you actually had enough chips to perform it, and the other is at the end of all the firings you got something stable. Okay, so you can ask, I give you a graph and an S and ask you, does it stabilize? And one thing you could do is just start doing some firings in some order and see what happens. But this might take a while. So there's a situation when that's a relatively okay thing to do. So that's the Eulerian case. So
Aren't you going to justify abelian first? Then?
yeah, okay, good. So you might wonder, like, well, maybe if I did this in a different order, then I could get a different result. So maybe there exists some finite sequence that stabilizes, but if I happen to choose some other sequence, I could go on forever. So it turns out that that doesn't happen. So yeah, so a lemma. So this is the abelian property. So if there exists a stabilizing sequence of length, say, m, then every legal sequence has length at most m.
Exactly.
So I'm breaking it up into, so legal means, I don't have to do all possible topplings.
Oh,
I just have to do, make sure each one of them is legal.
No, but just this statement, you could take the other sequence of shorter length and apply it, right?
So I'm not assuming this first one is legal, and I'm not assuming this second one is stabilizing.
Oh, God,
so
exactly. Very good, yes.
What is excluding for the what is legal?
So
But you have enough chips at the vertex to perform
So what is
the move.
stabilizing didn't imply?
That all of them are that all of the vertices are stable. You are in a situation where you cannot perform any move.
Each move was legal when you stabilized, when you did the stabilizing.
You can do only legal moves.
Right.
And at some point, either you run out of them or you
Right.
don't. Yeah. But
Yeah.
it's-
So, but sometimes it's useful to do illegal moves. That's why I want to break it up. So when I say there exists a stabilizing sequence, then I'm only requiring it to satisfy this second condition.
First condition may not be.
Right. So
So you might have negative.
I might have some negative chips at some point. Even at the end, I might have some negative chip values. But if there exists such a thing, then every legal sequence is at most as long as that thing.
So if you within the definition of stabilizing sequence, it is stabilizing and legal. Then, like what Avi said, if you flip it around, that means every stable legal sequence has then
That's the same length. Yeah, that's right. So
corollary.
right. So corollary, right, which is what you'll usually use, but sometimes it's useful to have this stronger version. So corollary, every legal and stabilizing sequence has the same length. And, well, you could say more. So if you wanted, you could.
So it doesn't help to have an illegal stabilizing sequence. You might as well always keep it legal, because if you had an illegal stabilizing sequence of length time, you would get a legal stabilizing one.
Right, right. So it doesn't help you stabilize faster to use illegal firings. It sometimes helps you in proofs, though, because it can be a pain to check in a proof that everything you're doing is legal, and this frees you from having to do that. So maybe I'll show an example of how that helps. But one comment I want to make is, so you can strengthen this a little more. So you could say, instead of just looking at length, let me look at, local runtimes. So I want to think of each vertex in my graph is like a little processor. And every time it fires, it's like, it has to do some work, okay? I want to know, like, how many times did it have to fire? So then instead of length, I get like a vector. So let's say, can you see blue?
Yeah.
Okay. So I could replace length by local runtime everywhere. So let's say local runtime u, and now u is a vector telling me this vertex fired 10 times, that vertex fired 25 times, and so on. And then it will be pointwise smaller here. And so again here you'll have every legal and stabilizing sequence. Not only do they have the same length, but they have the same vector of local runtimes. And in particular, a corollary of that is that if you stabilize, the final sandpile you get doesn't depend on the legal stabilizing sequence you chose. So sigma m does not depend on the choice of legal and stabilizing sequence.
So it's sigma m, or the last one. Yeah.
The last guy, yeah. So that might make you suspect that you can express sigma m as a solution to some optimization problem. So in the case of sandpiles, that problem is like it's an integer linear program. So one kind of equivalent way to state this first part of the lemma is that the local runtime, so this is the vector u, or the function u, whose value at vertex x is the number of times x fires in any legal and stabilizing sequence. So here, I should emphasize the S is fixed. So you're fixing S, and then that S will define this local runtime vector. And what problem is it solving? It turns out to be the following problem. So it's the pointwise smallest vector such that, so among all non-negative value, integer valued functions on the vertices, we would like to stabilize. So we'd like to start with our S and add Laplacian of this F and get something that's less than out degree minus 1. So it's an integer program, right? So you've got these unknown values, which are the values of F, the number of times I'm supposed to topple, and I've got some linear inequalities on that they have to satisfy, and then I take the pointwise smallest. So one picture I like to show, I'll draw it for you. I can show you on a laptop later. So, of course, a good instinct is to, if you see an integer program you're interested in, just relax it first to a real valued program and see what happens. And well, one particularly interesting choice of S is just a large pile of chips in, let's say, the square lattice Z2. Okay? So I'm working in the square grid graph. I start with, take n is abelian chips at the origin and stabilize them. So if I relax this program from natural numbers to real numbers, I'll get some kind of version of the sandpile model where I'm allowed to split up my sand grains into subgrains. I can divide them as finely as I like. And then what I get is some nearly circular shaped pile where, in Z2 my degree is 4, so I'm allowed to have up to 3 grains of sand per site, and I'll have exactly 3 everywhere in a nearly disc-shaped portion of the lattice, and then I'll have some very thin boundary strip where I'm, between 0 and 3, and then I'll be 0 outside. So that's what you get in the, the real valued version of this problem. If you do the original integer valued version where you're not allowed to split up chips, you get all kinds of extra structure in your picture. So first of all, you don't see a perfect disk shape. You see a shape with some kind of flat sides. And then on the inside of the picture, there are sort of regions where you're exactly 3, but there are regions where you see other patterns. So there are different periodic patterns in different places. So if you kind of zoom in on your picture in a particular place, you'll see different periodic patterns of sand. And you can classify these patterns, and that's a whole other story that I won't really talk about. But it's a good way to see visually the large effect of changing integer values to real values. Okay.
So just it's about the proofs of these lemmas are simple.
Yeah. Let me say in words the proof. Okay. So you induct on the length, and what you do is in your stabilizing sequence, you look at the first vertex. Or sorry, in your legal sequence, you look at the first vertex that fires, And that must occur somewhere in the stabilizing sequence, because if it didn't occur, there would be too many chips there at the end. So then you just argue you can, wherever it occurs, you could just bring it to the front and then induct, then cross them both off and induct. And you can ask, since this property is so useful, you can ask like, well, what did it really rely on? And there's two ways to think about that. One is, if you're thinking of the Laplacian matrix, what it relied on is the positivity of all the entries off the diagonal. So you would get in trouble if you had a toppling which removed chips from neighbors. The fact that you're toppling, it only removes chips from one side, it adds chips to all neighbors. That was key. And there's another way to kind of push this property to a more general setting, which is the abelian networks that I'll get to in the second part of the talk. Okay, so yeah, so let me tell you, okay, so the main question for like the next half hour, which will take us on this little tour of what you might call algebraic directed graph theory. The main question motivating us will be, given a sandpile on a directed graph, how do you decide whether it's going to stabilize or not? Okay, so first I'll tell you the Eulerian case. So that's a case where this question turns out to be easy. So if you think of Eulerian graphs, you're probably used to the undirected version of Eulerian, where in order to have an Eulerian tour that visits every edge exactly once, you need the vertex degrees to be even. But in the directed case, we're going to be interested in directed Eulerian tours. So those are, we want to visit every directed edge exactly once. And, well, if you think about that condition, so definition G is Eulerian if there exists a closed path visiting every directed edge exactly once. So instead of caring about the parity, what we're going to care about is, you better enter each vertex the same number of times as you exited it. Okay, so this certainly forces that the in degree of every vertex equals its out degree. And the other thing it forces is connectivity, right? So, in fact, strong connectivity. And then these two are actually equivalent to being Eulerian. So that's a lemma or theorem. Yeah. Okay. So Eulerian if and only if both of these conditions hold. So now I want to think of this condition kind of algebraically. So it turns out, it's easy to write this condition in terms of the Laplacian matrix. It's just saying that Laplacian of the all ones vector is the zero vector. And so here's, this was one of the first theorems in chip firing, actually even before Björner-Lovas and Shor. So Gabor Tardos in 88 showed if G is Eulerian, then S if G Eulerian, then your sandpile S stabilizes if and only if there exists a solution U of this problem. Let's call it star, satisfying U of x equals 0 for some x. Let's say min U equals 0. So you don't have to search, Tardos says, in this, potentially large space of all integer valued functions. You can restrict your search to ones that actually are 0 at some vertex. So what that's saying is you could just naively start firing in your favorite order, and if you ever come to a situation where every vertex has fired at least once, then you know you're never going to stop. And then he went on to show that in the Eulerian case, that will happen in polynomial time. So this gives you poly time. So either you stabilize in polynomial time, or you'll witness that you can't meet this condition. Either stabilize in poly time, or never. So
this if and only if statement is only for Eulerian graphs?
yeah. So it's natural to ask, like, what, where is this min 0 coming from, and what takes its place in general strongly connected graphs? So where it's coming from is very simple. It's coming from this restatement of the in degree equals out degree. So since the all ones vector has Laplacian 0, in terms of the sandpile, it's saying if I topple every vertex once, there's no net movement of chips. So every vertex will send out its out degree and will receive its in degree, and those are equal, so there's no net movement. And so, well, if you're looking for the minimum such function, you can always subtract a constant function from it and get a function that's 0 somewhere. So that's what's going on here. And it suggests that, well, for a general strongly connected graph G, the Laplacian will still have some vector in its kernel, just by construction, because it does have a vector in its left kernel. So the all ones vector is always in its left kernel. But it won't be the all ones vector necessarily in its right kernel. Okay. So not hard to see if you're strongly connected, then your Laplacian has rank, has co-rank 1. Okay, so there's exactly a one-dimensional kernel. So there exists a unique integer vector, let's say primitive integer vector.
Primitive, no common denominator.
Right. Which I'll call pi. Right, so primitive means the greatest common divisor of the entries of pi equals 1. And there exists a unique primitive integer vector in the right kernel, so such that delta pi equals 0. Okay, so what is this vector? You've surely seen it before in other guises. It's the PageRank vector for Google search. It's the stationary distribution of a simple random walk, where for every time step, you're at a vertex and you choose uniformly among your out neighbors and jump there. And one thing that's been rediscovered many times, but is still not as well known as it could be, is there's a combinatorial interpretation of this vector. So this sometimes goes by the name Markov chain tree theorem. And it says that
This is late on, or this is sort of, or many people realize this?
yeah, so I found, actually I should have written down the name. I found some reference from back to 1975, but I need to look up again. It was some biology paper, I think. And there's a reference from the 80s, and then the one that is more familiar to many of us is Aldous and Broder. And probably it was rediscovered after that. So let me state the theorem. So it tells you combinatorially what the entries of pi are. Let's see, pi v equals, let me call it kappa v over capital K or something, where kappa v is the number of spanning trees of your graph oriented toward V. So for each V, you can count how many spanning trees your graph has.
Yes, without direct spanning.
Yes, so all the edges of the spanning trees have to be a subset of your directed edge set, right? So,
But also point to the...
and they also have to point toward V, yeah. So the way I like to think of directed spanning trees is if they're directed toward V, you can think of them as a bunch of local choices. So it's a subgraph. It's a spanning subgraph. So you take all the vertices and some subset of the edges with, out degree of every vertex is equal to 1, except at V, the out degree is 0.
everyone chooses a parent.
Yeah, everybody chooses a parent, and eventually, if you follow parents, you end up at V. So maybe here's V, and if I want to think, so here's an undirected graph, a square grid, which is one of my favorites because it's easy to draw and very interesting for most sandpile questions. And if you want to think of an undirected graph in our setting, you just replace each undirected edge by a pair of directed edges. And then your spanning tree will look, so you choose an outgoing edge from every vertex, except not from V. So. Okay. So now you just orient all these to point toward V. Okay. So for each V, you can count these, and then you'll get some vector, which I call kappa, and that vector may or may not have GCD1. So I divide by capital K to make it have GCD1, and that's my unique primitive integer vector. So this capital K turns out to be an interesting number. So this is, by definition, the GCD of all the kappa V's. And the first place I could find this in the literature was in a paper of Trung Van Pham. So I called it the Pham index of G. And it's a curious kind of quantity. Why would you take the GCD of spanning tree counts? But we'll see that it tells you something concrete about your graph. It's measuring, in some sense, how Eulerian your graph is. So maybe for context, let me tell you a few things about Eulerian graphs and their duals, the co-Eulerian graphs. So
are you going to relate the number of spanning trees to the determinant? Or don't care about
No, that's how you prove it, but I don't think that we plan to do it yet.
yeah, but it does belong to the tour of the algebraic directed graph theory, right? So there's the matrix tree theorem, which says, kappa V is the determinant of, if you remove the row and column corresponding to V from the Laplacian, then that will count the number of spanning trees rooted at V. Yeah, that's worth mentioning. Okay. Okay, so we talked a little bit about Eulerian graphs, and with Matt Farrell we defined co-Eulerian graphs to be the ones where this Pham index is 1, K equals 1. And here's a very simple example of a co-Eulerian graph, or multigraph. So it's okay, so it's just a path with edge multiplicities 3 going to the right and 2 going to the left. And why is this co-Eulerian? Well, if you want to get a spanning tree rooted at V0, then you can choose, you have to choose all the leftward pointing edges, and so you have 2 choices at each stage, so you get 2 to the n of these. But if you want a spanning tree rooted at Vn, then you have to choose all rightward pointing edges, and so you have 3 choices at every stage, so there are 3 to the n of these. So these things have GCD1. Okay, so okay, so let me make a little chart here of what's going on in the Eulerian and co-Eulerian cases. So, okay, so in the Eulerian case, we already saw that the kernel of the Laplacian viewed as an integer matrix is spanned by the all ones vector. And co-Eulerian has the kind of dual property to that the image of the Laplacian is as large as it can be, so it's well, I guess you could call it 1 perp, so it's all the integer vectors that sum to 0. Now, in the Eulerian case, so something equivalent to this kernel would be the statement that all the spanning tree counts are the same. So the fam index is equal to kappa v for all v. And here we had kappa k equals 1. And okay, so let's assume, so for these equivalences, we assume strongly connected. Okay, so this is equivalent to, as I mentioned, G having an Eulerian tour. Okay, so what's the kind of global counterpart here, to the Eulerian tour? Well, one way, one manifestation of it is from the sandpile. So it turns out that sandpile S stabilizes on a co-Eulerian graph if and only if it has few enough chips to do so. So by pigeonhole, you can never stabilize if you have more chips than the sum of the out degrees minus 1. So this is certainly a necessary condition for stabilizing, but it's, on most graphs it's not sufficient, but on the co-Eulerian graphs it is. So this was initially surprising to me. The story behind this project was that Matt Farrell was a Cornell undergrad who came to me for a research project, and I like giving people some concrete problem that's the easiest thing I don't know how to do. So the easiest thing I didn't know how to do in 2014 was, how do you decide if a chip configuration on this particular graph stabilizes? And then So I gave Matt that problem, and he came back to me, pretty quickly and said, "Oh, you just have to count the chips." And that I was sure he was wrong, because in my experience with graphs like the square grid, counting the chips is far from answering stabilization. But it's true on this graph. All you have to do is count chips. So that got us interested in, how common are these co-Eulerian graphs? And we didn't know the answer back then, but thanks to this recent paper of Nguyen and Wood, we know they're pretty common. So if you just take a random graph on n vertices and a number p strictly between 0 and 1, and you just put each directed edge present or absent present with probability p independently, then this thing will be co-Eulerian with some pretty substantial probability in the limit as n goes to infinity.
I would have expected it to be probability 1.
Okay, so Avi says he would expect probability 1 to be co-Eulerian, because
I know you know it's just because why should the GCD be anything different than 1? The number of spanning trees, why should they have a common divisor? I know the answer from your abstract, but
right.
I would have expected, you asked me, I would expect this would be the typical situation.
Well, okay, so let me write so it's in the abstract, but it's this funny expression in terms of Riemann zeta function. Which comes out to about 43%, so as n to infinity. Okay, so
that's not bound, that's exactly the probability in the limit.
That's exactly the probability in the limit, right? And I mean, I could tell you where the number comes from. The proof is much harder than this, but where it comes from is considering each prime independently. So you have GCD1 if and only if you're not divisible by 2, you're not divisible by 3, etc. Now, if you work for each prime, you can work over that finite field, and then you can ask, what's the chance that the Laplacian has a kernel when considered mod p? And if you multiply all those probabilities together, you get this number. So the hard part of the proof is somehow justifying that, that computation. That why do the primes really act independently? Okay. And in terms of the intuition that most, it should be 1, I don't know. I mean, it's true if you chose some large numbers at random and took their GCD, then it should be 1. But yeah, like in the Eulerian case, right? And this it's not completely obvious, if you just to give an elementary proof that for an Eulerian graph, the number of spanning trees oriented toward V doesn't depend on the choice of V. So that's like the opposite situation.
Yeah, I agree.
So.
Just that, in a random graph, this pi will be just some weird vector. It will not be the uniform distribution like on the. Eulerian is uniform.
Right.
Yeah, but this pi will be some non-uniform vector, which I wouldn't assume unless I knew otherwise. There's a reason for some.
Yeah.
But this explanation is probably convincing. And then you have to figure out that these numbers actually don't multiply to give you something close to 1, but they actually happen to be something else.
Right. Okay. So you might ask if it's easy in the Eulerian case to determine stabilization, and it's also easy in the co-Eulerian case, then maybe it's just always easy. So Matt and I thought about that for a while, but it turns out, so there is some intermediate regime where it's hard, but in a slightly unsatisfying way. So this is where multigraphs will become important. So
in the multigraph case, you pass 2 chips to the neighbor if there are 2 edges and so on.
That's right, yeah. So I probably should have written it more precisely, but if
But
you have
you
2...
send along every edge that you can, 1 chip.
That's right, yeah. So in the multigraph case, like in this graph, when you fire V1, you send 2 chips to the left and 3 chips to the right.
Can you say when it's stabilized in polynomial time?
Yeah, so, okay. So, yeah, there's 2 distinct questions, right? One is, how long does it take to stabilize? And the other is there a fast decision procedure for deciding whether it stabilizes? So like already for this graph up here, it can take exponentially long to stabilize. Like if you start with the maximum, start with this number of chips, the maximum allowable, but you put them all on which end? Either V0 or Vn is going to be hard. I guess Vn is going to be hard. So it's hard for chips to get from right to left in this graph because the edges are all sort of pushing them to the right. So if you start with this number of chips on Vn, it will take you exponential time.
It's the usual example for you take random walks on directed graphs. If you
Mhm.
have edges pointing, and they all point backwards. So
That's right, yeah. But at least for this graph, you just count chips to decide stabilization. So, but unfortunately, or I don't know if it's fortunate or not, but the reality is for strongly connected multigraphs, so this is the theorem with Matt Farrell. Strongly connected multigraphs, it is NP complete to decide whether a sandpile stabilizes.
NP complete is actually also an NP, which is not obvious also.
Right, so why is it an NP? Basically because of this formulation. So if it stabilizes, then I can tell you, a particular function f, which stabilizes it, and then you can just verify that f obeys these inequalities.
But you need to somehow bound the maximum value of the.
Yeah. Okay. Yeah. So the f won't be too enormous. Yeah, okay, you need to do some work, but f can be exponential in the number of vertices, but it can't be more than that. But yeah, there's a little bit of work there. So we proved this, but I'm kind of unsatisfied with the outcome because it's very heavily dependent on it being a multigraph. So basically, how do you input a multigraph to your decision procedure? You give the adjacency matrix, okay, which could be full of very large integers, right? And so.
But this is NP complete in the usual sense, in the description of the. Yeah. It's
Yeah.
In the description.
In the description of the problem.
Description of the problem.
Right.
So in the proof, you really need multiplicities that are bigger than exponential in the number of vertices.
I don't know about bigger than exponential, but there could be multiplicities that are exponential. So
Okay, so binary, they will be the same order as the number of vertices.
right. So if you kind of trace through the reductions, we reduced to some problem about lattices called non-negative rank, and that in turn reduces to knapsack. And so knapsack is one of these problems that's hard because the input could be large. And I don't know though if this problem is of this type. So, an open problem which I would love to know the answer to is, what about simple directed graphs?
pseudo-polynomial time algorithm? Like, pseudo-polynomial means that, yeah, in the unary description of the entries of the matrix. Polynomial in the unary.
Yeah, I have to think about that. So I can tell you how the reduction goes from, so it goes from, sandpile stabilization reduces to this non-negative rank. So, and then this thing eventually gets to knapsack. So I have to think about this step of it. So this reminds me of a quote from Peter Winkler that real men reduce from sat. He said this at a lunch one time when he was speaking in our seminar at Cornell, and it was him, his wife, and me and some students. And the students and I burst out laughing when he said this, and his wife was just like kind of puzzled, like what was funny about this? It's like sort of hard to explain why it's funny, but I don't know. Somehow you get more information if you just read it from SAT. If you go through some long chain, then it's harder to see what's going on. Yeah, so let me think offline about your question. But I guess I could mention one general fact we used in the reduction that could be useful. So Perkinson, Perelman, and Wilmes. So for any lattice, or for any, let's say, subgroup of Zn of rank, let's say of codimension 1, there exists a directed multigraph G such that you can write your subgroup as the image of the Laplacian of G. So, I mean, this to me is like a really useful observation. So, like, you just abstractly, you have some subgroup of Zn. You're just given it in terms of some basis or something, and all you know is that it has codimension 1. Then you can always find a multigraph such that your subgroup is actually the image of its Laplacian. So it really lets you transform some abstract, algebraic thing into a concrete graphical thing.
And here the multi is also large.
The multi is large. Actually, it's funny. So one thing we were stuck on in proving this for a while was how to prevent the edge multiplicities from blowing up too much in this lemma, because it's not clear if you just naively apply their proof, then they could even be bigger than exponential. But there's a very simple trick for preventing blow up, which is that you can always work, in all the operations, you can always work modulo the determinant of this lattice. So I guess you have to define that properly, for instance, codimension 1. But anyway, okay, we needed a sort of full rank version of this, which I'm not writing down, that, well, if you have codimension 0, then in place of the graph Laplacian, you put the graph Laplacian with one row and column removed. And then, it has finite index. That's what I call determinant of L. And you can just always mod out your entries by this, and it never affects anything. So that's the simple trick for preventing blow up. Maybe it's a good time to break, and okay, so Guy reminded me that I didn't say anything about rotors or the best theorem, which that would leave the tour of algebraic directed graph theory incomplete. So, and it's a good lead-in.
You have to decide. You have lots of things that if you want.
Yeah. So
definitely, it would be nice if you talk some about the network.
Okay. So I'll keep it to 5 minutes as a lead-in to the abelian networks. So. Right. So let's think of our graph now. Each vertex is some limited automaton. Okay, and the sandpile is one particular automaton. So you can think of it, if you have a vertex of out degree 3, then my automaton, it needs a little bit of memory to remember modulo 3 how many chips it received in the past. And then every time that number becomes 0 mod 3, it says, oh, I now have enough chips to send one along each outgoing edge. So if you give each vertex 3 internal states, then you can implement the sandpile with an automata network. And we'd like to know kind of what is the general class of networks that have this abelian property. And here is
That property means it will not depend on the order.
right. So yeah. So what I'm gonna tell you is a local condition that you can check for each automaton individually, which will imply that globally, if you do a whole bunch of things, it won't depend on the order. So before I give you the general definition, let me tell you kind of the next most studied case after the sandpile. So rotor networks. So the sandpile, you had this directed graph, and that was kind of all the data you needed. For rotor networks, you need some additional data. So you need an ordering of the outgoing edges from each vertex. So suppose I give you this data, and so here's edge 1, edge 2, and edge 3. And now instead of releasing my chips in batches of 3, I'm going to release them as soon as I get them, but I'm going to use this ordering to decide where to send them. Okay? So if this vertex V was a rotor, then that you could think of it as it's an automaton that has 3 internal states, and you could think of the internal state as a little arrow pointing along one of its outgoing edges, and that arrow tells you last time a chip was sent from V, which way did it go? Okay, and then the update rule of the automaton is, well, if it receives a chip, then it advances to the next edge in the ordering, and then it sends the new chip along that edge. So basically, so a rotor sends chips one at a time in this fixed order according to let's call this? I don't know. Okay, so you could consider, well, what happens if I have a network of rotors that's all hooked up to each other? If I drop one chip into that network, then, well, so what do I need to specify? I need to specify, like, the current state of each vertex. So, so the state of the network is, let's say there'll be a single chip at some vertex, I don't know, V star, and local states, rho V, and V. So the local states tell me where I am in the ordering of each vertex. Okay, and then I could just trace what this chip does. So for at each step, I'm gonna, so one step. So this defines something called rotor walk, which is some naive de-randomization of a random walk, if you like. So so you look where the chip is. It's at V star. You first advance row of V star to point to the next edge in the ordering. To next edge in the ordering. And then you follow that edge. So chip follows that new edge. So you'll get a walk where, at every step you're updating one of these little red internal states and you're moving your chip to a neighbor. And so here's, in this language, a restatement of an old theorem called the Best theorem. Best stands for De Bruijn, Aaron Voigt, Smith, and Tutt. Eventually, so let's say if the red edges form a spanning tree oriented toward V star, then the rotor walk will just repeatedly trace out an Eulerian tour of the graph. Repeatedly. Well, I guess I need G to be Eulerian, so suppose G is Eulerian. Repeatedly traces an Eulerian tour. So like, I don't know, if you had a graph like this, right? So we want to consider it as a bi-directed graph. So
We point them clockwise.
right, and then, well, we need to choose a cyclic ordering. So since we're in the plane, let's choose clockwise, right? So then the rule of the walk is wherever my walker is, so say my walker is here, I have a spanning tree of red edges pointing to my current location, and then I have one more local state, which is the local state at my current location. So maybe that points here. So this is V star, and this is rho V star. So if I repeatedly cycle my cycle my rotor clockwise and then follow the new rotor, then I'm going to do an Eulerian tour of this grid, which remember means every edge will be traversed once, both backwards and forwards. Now the way you usually state this best theorem is as an enumeration if you want to count Eulerian tours. So this gives you a way of counting them because it gives you a bijection, right? So if you perform an Eulerian tour, well, the red edges will tell you what you did last. Every time you exited a vertex, what was the last place you went. So if you pick a starting edge for your Eulerian tour, this yellow edge, and then run the whole tour and see, well, what was my last exit from every vertex, you'll get a spanning tree rooted to your current location. You can't get cycles because it's the last exit. Last exits go forward in time, so they can't form a cycle. So the way you usually would state this is, you get a bijection from spanning trees oriented toward V, and then the other thing so that's the red edges, and the other thing you have to specify is, this ordering, right? So the red edge is going to come last. So what you have remaining is like a cyclic ordering. Cyclic orderings of the outgoing edges of W for all W. And that bijects to the Eulerian tours. So you have to be a little careful about where you're starting your tour. So I fixed a starting vertex for the spanning tree, so I should fix a starting edge for the tour. So starting with a particular fixed edge. Edge. B star. Right. So, in particular, if you want to count Eulerian tours, you have this determinant that counts spanning trees, and you have some factorials that count these cyclic orderings. Okay. Yeah, so, well, okay, you have to decide what you want to be finite, right? So, so let's talk about just abelian processors in general. So, so for me, let's say an abelian processor with, input alphabet so it has an input alphabet and a state space and an output alphabet. And so it's going to be an automaton that can read letters from A, change its state, and then send letters in B. But it should do so in an abelian way. So what is it? So is a collection of maps So there are two types of maps. There's the state transitions that tell you if I read a letter A and I'm in a particular state, then I'm going to transition to some new state. And
For really like,
yeah, for little a in A. And then there's an output map that tells me if I read a letter A and I'm in a particular state, then I'm going to send 0, 1, or more letters from my output alphabet. So these are the state transitions, and these are the output. So TA of Q will be some Q prime that says if I read an A and I'm in state Q, then transition to state Q prime. OA of Q will be some vector X that says if I'm in state Q and I read a letter A, then I should send that vector. So here I'm putting, you might expect to see words here, right? But I want to be in the abelian setting. So I'm in a setting where like all I can do is I have a pile of letters and they didn't come in a particular order, or if they did, they might have gotten scrambled. And so all I can do is count how many of each type there are.
and there's some legality condition.
Right, okay. So
Not always can you perform every one of these.
that's right, yeah. So how do you put legality in the picture? So so that comes when I kind of wire these things together, right? So now I'm going to say an abelian network. Let's see. Okay, but maybe I should say, right. So I want these maps to satisfy some commutativity, right? So I would like, if I receive an A and then I receive a B, that I get the same state as if I received them in the other order. Okay, and I'd like to say if I receive an A and then a B, then I output the same multi-set of messages. So that corresponds to saying, well, if I receive an A, I'm going to output OA. Then if I then receive a B, I'm going to be in some new state, OB. So I'll get OBTA. And then if I did this in the other order, I'd get OATB plus OB. Okay, so these are like the axioms, if you want. But one interesting thing that's going to happen is for most of the examples we know and care about, they're of a particular form where the input alphabet is just a single letter. We're going to consider big networks, but where for each processor in the network, A is just a single letter. So note, okay, so I'll say it's unary if there's only one letter. And if there's only one letter in your input alphabet, then both of these conditions are vacuous, right? There's nothing to check. Right? So you can build non-unary abelian processors, but most of them come from networks of unary ones. Okay, an abelian network, let's say on a directed graph, is, well, a collection of processors. Let's say PV, where so at each vertex we'll have an abelian processor. And I'd like to restrict it to only send messages to its neighbors. So let's say it has input alphabet AV and some state space and an output alphabet the union of A W's where VW is an edge. So I want to think of the alphabets as disjoint, right? So each vertex has its own alphabet, and it's allowed to, those are the letters it can read, and then it's allowed to send letters in the alphabets of any of its out neighbors. And so you could picture this thing like you've got some vertices that are hooked up somehow. Maybe there are cycles, so these, V1 could send messages to V3, and V3 can also send them back to V1. And maybe there's also some, this network might be a piece of some larger system, right? So maybe the user is sending, input to this network, and then maybe there's some other edges by which the network is communicating output. So
the way we think of Boolean circuits, it's exactly like this.
yeah. So it's a circuit, and we'd like to just see what circuits can do when you have this abelian restriction, right? So one initial observation is like, well, what can a circuit like this compute? It's not really well set up to compute Boolean, valued functions. I mean, it can do that, but then you can keep feeding it more letters, and then it might output more. And so it's kind of the natural setting to think about what it computes is, it gets a multi-set of letters as input, and it gives another multi-set of letters as output. So, so you can think of this as computes a function So let's let A be the total, the total alphabet. It's the disjoint union of all the processors' alphabets. So that's like allowing a very powerful user that can just input letters anywhere he wants. And then we'll specify some set of output edges. So this is where we read the output. And usually one output edge is enough. I mean, you can, it's not really much more general to consider more. So we like to say, like, well, what kinds of functions can you compute with this kind of network? But so before telling you about that, let's just address the abelian property. So we've assumed local abelianness of each processor, but and then if you trace through the proof of abelianness for the sandpile, the same proof shows kind of global abelianness for a network of such processors. So there's a bunch of kind of local to global theorems. So that basically say if each PV is something, then the whole network inherits that property. And the first such thing is abelianness itself. So if each PV is abelian, then let's see, for a network N, which is composed of processors PV, then N is abelian. Okay, so what does this mean? It means I want to like black box what's inside this circuit here and just say, well, if I send a letter, say, along this input edge, that might cause a lot of activity. Maybe V2 sends some messages, and then V3 sends some messages. A whole bunch of stuff happens, and then I get some output. And So I want to view the whole, internal state. The whole internal state I can think of, well, I just tell you the local state at each vertex, so it's a Cartesian product. So I'd like, if I drop two messages, right? So I drop a message, I do all the processing, and then I look at the state. And I drop another message, do all the processing, and then I look at the state. I'd like those two things not to depend on order. That's verifying this axiom. And likewise, if I did that, I'd like the outputs not to depend on order. So that's what this is saying. And if you trace through, it's the same proof as for the sandpile. It's, it's more notation, but it's true for the same reason.
But I'm just wondering, there is something called the Church-Rosser property in programming language. In the early days of, they worried about especially in distributed settings. When do you have a bit? I mean, when is an operation happening here and happening here in different orders? It doesn't affect the events. So there are very general theorems about when these kind of things hold from the days of Church and Russell, so the 40s, the early computation.
Yeah.
So it seems to me that these would be special cases, but do you know about this?
Yeah. So, I mean, you think this is a special case of Church-Rosser?
I think that Church-Rosser aims to just tell you in which most general setting, things are not necessarily defined as automata. I mean, there are processes. I mean, there are processes. They are infinite. I mean, the main game there, like in many of the programming language and logic situations, are infinite. But that it's not only forever. These are always maybe stopping in finite time. Anyway, it reminds me of this.
Yeah.
I don't know what would be more general, but it seems to me.
So there's this diamond lemma situation.
Yeah, exactly.
Yeah. So it's, I mean, it's the same kind of phenomenon. Yeah. 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 Okay. So.
Maybe it's the same.
It's a case of the diamond lemma. So, right. Yeah. But there are lots of other principles of this sort. So, like, for example, it turns out if each processor is a rotor, then the whole network is a rotor. And so where's the content of that statement? I mean, it's kind of, right, so imagine each of these is a rotor. So, I drop a chip, and the chip does some rotor walk on the inside, and it picks an output edge to come out. And then if I keep dropping chips over and over again, say along the same input edge, well, they're going to come out different output edges in some sequence. And rotors have a periodic output sequence. So it's saying, if each of these little things has a periodic output sequence, then the whole network will. And that's almost obvious. I mean, it's obvious that it's eventually periodic, right? But what's somewhat non-trivial to prove is there's no initial transient segment. If you're all rotors, then your whole network will be.
Is it possible that,
and so there are more things of this form waiting to be discovered. So there's a little time reversal argument that says if the fundamental period of each rotor in your network is a palindrome, then the same will be true of the whole network.
Actually, who defined the abelian networks? I remember a whole paper of Peter Winkler, but did you define it?
So, well, it depends how you want to think of it. So I was inspired by Deepak Dar, who has a survey on the physical motivation of sandpiles, and he has a paragraph in there about how one could define them. And then, with Ben Bond, we developed this, we kind of spelled it out.
I see also that Peter and his students think is more recent than like I don't know, 6-7 years ago. Properties, computability properties of of the abelian networks.
So, yeah, so with Peter and with Andrew Holroyd, we defined these abelian logic gates. So it might be after that there's a whole bunch of good student problems in there. So it might be after that they followed up on it. So, okay, and there's some more of these. So like for example, if each PV is irreducible, meaning that for any pair of states you can get from one to the other by by sending an appropriate input, then the same is true of the whole network. This requires the strong user that can really, put input wherever he wants. Okay, and I'm sure there are more of these. So you could think of these as kind of they're telling you they're kind of lower bounds if you want. Like a network of rotors is not going to compute anything more than just other rotors. So of course it can compute rotors of bigger period, right? So you could have rotors of period 2 or 3 on the inside, and then the whole big thing has a very long period. So, okay. So let me tell you about the logic gates for these things. So well, okay, there's one preliminary thing for this. So, you need to, you might worry about halting, right? So if you have a lot of feedback in your network, then maybe it just keeps sending itself more and more messages, and you never halt. So so as we saw in the first half of the talk, if you want to decide halting for a particular input, that can be a hard question. I mean, it can be, NP complete to decide it, even for sandpiles. But if you want to decide,
input would be the sandpile would be S, right?
Yeah, your input would be S and the description of the network, and you want to decide whether it halts. But here's a softer question. I've given you a network, and I want you to tell me if it halts on all inputs. Okay? And so it turns out this is easy to decide in the following sense. So n halts on all inputs if and only if you can write down a matrix so okay, I assume this guy is irreducible. So P is a matrix which is indexed by the total alphabet A, and the entry PAB is just a local thing. So I count number of A's produced by an input of n B's, but just locally. So let's say B belongs to some particular processor's alphabet V. So I just look in that processor without worrying about if it's going to cause any avalanches elsewhere in the network. I just feed that processor a large number of B's, count the number of A's, normalize. So I wrote this as a limit, but you can also write it as a finite average over just the state space of processor V. And so you take this matrix, and it's a non-negative rational matrix, so it has a Perron-Frobenius eigenvalue, and that's this lambda. So saying sort of if on average you're producing less than one output per input, then that will be true kind of in a stronger sense, that you'll halt on all inputs. And
otherwise, if it's one, it will give you the
Yeah,
One,
so
but it will be somehow periodic.
yeah, so it can be equal to 1, it can also be greater than 1, right? So if it's equal to 1, then yeah, there will be some input and some execution rule that will be periodic. If it's greater than 1, there will be some input and execution rule that makes the total population of letters explode. Yeah. And in this case, you can estimate also how long it will take to halt, and that's also just linear algebra. So in this case, if you want to know the runtime, let's say R, so it depends on the input. So X is a vector of letters that you input, and Q is a vector of states. And what you should do is take the identity minus P inverse applied to X, and that will give you a good estimate for the runtime. So like this thing is bounded by a constant that only depends on the network. It doesn't depend on the states or the particular input.
So what is this matrix for the sandpile?
Right. Okay. For the sandpile, and also for rotor, it has the same production matrix P. Let's see. So P will be
Exactly the adjacency matrix of the graph.
yeah, it's adjacency matrix normalized by degrees. So all right, so it's something like T inverse A. So right, so if I have degree D and I receive n chips, then I'm only going to output n over D chips to my neighbors. Yeah. Okay, so we know which networks halt on all inputs, and given such a network, we'd like to know, what kind of function can it compute in this sense, and can we sort of compute any such function by a simple circuit of a simple set of gates? Okay.
Computationally efficient to compute P because of this limit?
Yeah, so this limit makes it seem like something that could be hard, but yeah, as long as your processor is given by, so this thing can be replaced by some finite sum over the state space of processor V. So, in most of the examples we are interested in, like sandpiles and so on, this state space is tiny, right? So yeah. Okay, so let me write down the gates. So starting from the kind of most trivial ones, so the splitter. So this maps n to n squared, and it just doubles the input. And the adder, this maps n squared to n, and it adds the two coordinates. Okay, then this, in some sense, this is the real interesting one. So P Topler maps n to n, sends x to the floor x over P. So this thing is very similar to a sandpile. It waits until it receives P chips, and then it outputs one chip. So a sandpile would be kind of P of these combined, right? So sandpile, outputs, P times floor of x over P, because when it receives P, it outputs a batch. And then, okay, there's delayer. It says, don't do anything on your first message, but then just let everything pass through. So x minus 1 positive part. And presync. says only let the first thing through.
Are you writing a basis for all the, this will be a basis for all?
Yeah, so the theorem, yeah. So yeah, so the theorem is going to be any abelian processor can be, there's a directed acyclic network containing only components like this that computes the same function as that processor. So let me write a couple more columns here. So, well, okay, there's a number of states. It's sort of an interesting statistic. So the splitter and adder don't need any internal states. The p-Topler has p internal states, and each of these needs 2 internal states just to know whether it got one input or more than one input. And okay, these 3, if you just consider networks of these 3, you can get what we call ZILP functions. And if you allow them all, then you can get what we call Xylep or any Xylep functions. So what's ZILP and Xylep? Yeah, I'll end with this. So, so ZILP stands for.
Why are Boolean gates like ends and also just plus sometimes not? Well, I guess plus is there, so it's.
Okay.
What's wrong with that?
What's wrong with the usual gates? Yeah. So, yeah, I wrote in the abstract that the usual abelian gates aren't, or the usual Boolean gates aren't abelian, but maybe what I should have written is there's no way to make them abelian with a finite state space. So it's true that if you wanted to model an AND gate, right? So AND, is just some Boolean gate, right? But if we wanted to kind of lift it up to be natural numbers, well, you could, for example, take minimum, right? So minimum acts like AND on its Boolean inputs. So that's a perfectly fine, this guy is, there is an abelian processor that computes minimum, but infinite state space. Because somehow, if you receive 1,000 of inputs from one wire, you need to really remember that you received 1,000 in order to be able to take the minimum with the other wire. So, yeah, so that's what's, if you want to build a circuit where everything is finite, then this will do it for you. It's interesting, by the way, to ask, suppose you allow circuits of, finite abelian processors and mins. What can those compute? So there are all kinds of follow-ups you could ask for. Okay, so ZILP stands for 0 at 0. That's the Z. What does I stand for? LP stands for linear. Oh, increasing. Yes. Okay. X less than or equal to y implies f of x less than or equal to f of y. Vectors. Yeah. So coordinate-wise inequalities, and LP stands for linear plus periodic. F equals L plus P, where L is linear and P is periodic. So one thing that can happen, of course, is, if you take a function like floor x over 2, well, you can write it as a linear part plus a periodic part. But of course, both of these parts will involve rational numbers, right? So So, in this decomposition, L and P are no longer integer valued. Okay. So, and Xylep is the same thing, except but you relax the condition on P. P only needs to be eventually periodic. So, okay, and so the theorem. So the theorem is that any finite abelian processor computes a Xylep function. Well, that part is sort of obvious, because if the state space is finite, you have to get some periodicity from that, and any Xylep function can be computed by a network or a circuit of these gates. Yeah, so this is me and Holroyd and Winkler. So one interesting thing is, it's an infinite list of gates. So, I can consider a p-Topler for any p, and it's easy to see you can restrict to prime p. Because if you want p to not be prime, you just factor it and put a bunch of Toplers in series. But you might ask, well, I only want finitely many gates. What can I do with that? And the answer is any finite set of gates is not going to suffice to compute any Xylep function, because well, you can pick some prime that each of your gates will have some kind of fundamental period where if you put that many, if you put an input that's a multiple of that of this number n, then it will act as the identity function on its internal states. And so, if you take finite set of gates and you take the product of all the fundamental periods of those gates, then you won't be able to compute a p-Topler where p is, co-prime to that number. So you need infinitely many gates. However, that's with the usual paradigm of directed acyclic circuits. And one kind of nice thing about these networks is, all these theorems apply even if you have feedback. So you may as well try to use the feedback. And indeed, if you just allow a little bit of feedback, you can do without without most of the Toplers. So I'll leave you to think about this. So if I put two Toplers in series, right, then this guy will be like a 4 Topler. So this guy acts like. So if I put 4 things in the top, I'll get 1 thing out of the bottom. But how would I get a 3 Topler? Well, if I add an edge like this, so what this means is I split the output of this 2 Topler. I send one to the final output, and I send the other back up here. Then, instead of a 4 Topler, I'll get a 3 Topler. So you can emulate 3 Toplers by networks of 2 Toplers, and in fact, you can emulate any Topler by this kind of trick, if you allow.
The multiplicity is going to be large.
The multiplicity.
So the edge is going doing
Oh.
multiple ends.
You can do it with this, even with a simple network. So what you do is let's say you're aiming for an n Topler.
It's like a binary representation.
Exactly, yeah. So you take the binary representation of n, and then you use that to decide, which backward edges to do, and then you can get any n Topler that way. So you don't need multiplicities for this. Okay, well, there's more to say, but it's a good place to stop.
All right. Thanks.
Thanks.